We see many things around us. What makes it possible for us to see them? At night, when we switch on the light, we can see the books on the table, the clock on the wall, the clothes on the stand. But we cannot see anything if the lights are off. We say that light makes things visible to us. Can we see the entire book when the light from a table lamp falls on it? No. We only see those parts on which the light falls and get reflected into our eyes. When traveling in a bus, you must have seen its windscreen, the big glass window in front of the driver. It is always clean. But do you notice it easily? No, you don't. It is because light rays pass right through it. We easily see a vehicle in front of the bus through the windscreen, but not the windscreen itself. Look carefully at a beam of sunlight entering through the roof. You see a spot of sunlight on the floor. In the beam, you see dust particles moving randomly. In fact, it is because of these dust particles that we can see the path of light. What is this path like? It is always straight. This is called the propagation of light. Light travels in a straight line. This is called the linear propagation of light. Let us verify this property of light through the following experiment. Nowadays, we get laser torches that give red light. This torch gives out a fine beam of light which travels very far. Shine this beam on a distant wall and obtain a spot of red light on the wall. You will easily see that the path of light is a straight line. Let us take a look at another experiment. Take a 1/2 meter length of plastic tube with a diameter of 1 centimeter. Look through it at some object. Now, bend the tube a little. Can you still see an object? No, you will not be able to see that object now. At first, when the tube was straight, the light rays coming from the object could travel through it and enter your eye. However, now that the tube is bent, that is not possible. This tells us that light travels in a straight line. Let us verify how light travels through another interesting experiment. Take 3 square pieces of cardboard as shown in the figure. Make a fine hole exactly in the center of each of these pieces. With the help of stands, place these squares one behind the other at intervals of 1 meter. Take a long stiff wire and ensure that it passes through all 3 holes. Place a lighted candle at one end in front of the hole. Now look through the hole in the cardboard at the other end. You will easily see the light from the candle. Now move any one of these 3 cardboards slightly. Do you see the light now? You do not. It is because the 3 holes are not in a straight line anymore. This shows that light always travels in a straight line. You might have played at casting shadows of the shape of a dog or rabbit or bird in the light of a lantern with the help of your hands and fingers. How does an object cast a shadow? Let us see the formation of shadows. We saw light travels in straight line. When the light is broken with opaque objects like our hands, the shadow of the object is seen on the wall. This happens because the light could not reach the wall through our hands. Let us see how shadow is cast by a point source of light through the following experiment. Take a candle, a bulb or a torch as a source of light. Place a piece of cardboard with a hole in its center in front of this source as shown in the figure. Now, the light can be seen emerging from the fine hole O. Such a source of light is called a point source. At a distance of about 1 meter in front of the cardboard, place an upright screen. Between the source O and the screen, suspend a ball PQ as shown here. Now observe the shadow AB of the ball PQ. The rays OP and OQ from the point source pass the ball just touching it at P and Q and fall on the screen at points A and B respectively. However, no rays reach the part of the screen between A and B. Hence, this part remains dark. This is the dark shadow called the umbra. Let us try an experiment in which a point source of light is removed. We do not have a point source of light anymore. This is called an extended source. Children, imagine the nature of the shadow caused by an extended source. In the figure alongside, MN is an extended source. PQ is the ball placed in front of it. As a result of the extended source, we see a shadow which has two parts, a faint part and a darker part. The part BC, which is fainter, it is called the penumbra. AD is the darker part and it is called the umbra. Keeping the distance between the extended source and the ball same, move the screen further away from the ball. Observe the shadow of the ball. As the screen moves further and further away, the umbra becomes smaller and smaller till it completely disappears. This shows why an aeroplane or a bird does not cast a shadow when they are very high above the earth. Eclipses. We saw how, when there is a source of light, an object casts a shadow on a screen. The sun is a large source of light in the sky. The planet Earth and its satellite, the moon, are also in the sky. Why do we not see their shadows? Because there is no screen on which these shadows can fall. But when the sun, moon, and earth happen to come in a straight line, we say that an eclipse has occurred. If the moon comes between the sun and the earth, and the three are in a straight line, the shadow of the moon falls on the earth, and we say that a solar eclipse has taken place. A solar eclipse takes place only on a new moon day. The solar eclipse may be total or partial. If the earth comes in between the sun and the moon, and the three are in a straight line, the shadow of the earth falls on the moon, and a lunar eclipse takes place. Naturally, a lunar eclipse takes place only on a full moon day. It may be either total or partial. Let us study another interesting concept of the colors in sunlight. We generally see sunlight as being yellowish-white. However, we are not aware that there are many colors mixed in it. While painting a house, the painter uses a white base to get the desired shade. Let us try to understand through this experiment that white color has many colors. Cut out a circular piece of cardboard having a radius of 1/2 meter. Make a hole in its center and pass the spoke of a bicycle wheel or a long nail through it in such a way that this disc will be able to turn around it. Draw 7 lines from the center to the periphery at equal intervals so that we get 7 equal triangles on the circle. Color the triangles violet, indigo, blue, green, yellow, orange, and red respectively. Now, holding the nail in your hand, turn the disc. While the motion of the disc is slow, we can see the different colors distinctly. But when the turning disc reaches a certain speed, it appears to be white. This tells us that when 7 colors are mixed together, we get white. We saw how we get white from 7 colors. But is it possible to get the 7 colors from white? Let us try. Take a glass prism. It has 2 triangular sides. Take a cardboard and make a fine hole in it. Do this experiment in a room where you get a beam of sunlight from a window. Close the window in such a way that you get a single sunbeam into the room. Place the prism on a table with its base facing you. Make sure the room is dark enough. Through the hole in the cardboard, allow the sunbeam to fall on the prism at a slant. Now look from the other side. You will see a band of 7 colors called the spectrum. If you allow the spectrum to fall on a white screen, you will see the 7 colors distinctly. You will see the red color at the top of the spectrum and the violet at the bottom. In between, you will see orange, yellow, green, blue, and indigo in the order. This tells us that sunlight can be broken up into 7 colors. Have you seen these 7 colors of sunlight anywhere else? Sometimes, after a shower, if you are standing with your back to the sun, you may see the arch of the rainbow in the sky in front of you. In the rainbow too, you will see the red color at the top and violet at the bottom. We see a rainbow when the sun's rays pass through the raindrops in the sky. It means that the raindrops, like the prism, break up sunlight into its 7 colors. Children, let us now prepare the pinhole camera. You have seen that light travels in a straight line. Using this property, you can easily make a special camera of your own. Take a square or round cardboard box. The box used for keeping shuttlecocks would be ideal. Remove one lid and in its place cover the mouth with a piece of white kite paper. Make a fine hole in the center of the other lid of the box. Light a candle and place it so that its flame will be directly in front of the hole in the base. Now you will get an upside-down image of the flame on the kite paper screen. Do you know why? Because light travels in a straight line. The upper part is seen at the bottom and the lower one seen on the upper side. It is clear from the diagram that the image of the flame is inverted because of the linear propagation of light through the hole. We know that plants use light to prepare their food. Light is necessary for the growth of plants too. Let us verify this through this experiment. Take some soil in 2 small dishes. Plant about 25 grains of wheat in each dish. Place one dish in complete darkness. Place the other where it will get plenty of light. Water them little every day. After a week, observe the two dishes and record your observations as shown in the following table. It was observed that the height of plant kept in the dark was short, while the plant that received sunlight was tall. Color of plant kept in the dark was yellowish green, and the color of the plant that received sunlight was deep green. Even the condition of the plant that was kept in dark was weak, while the plant that received sunlight was strong. These above points tell us that light is necessary for the growth of plants. What is the effect of different colors of light on the growth of plants? Let us see through this experiment. Take red and blue cellophane papers. Take some soil in 3 beakers and plant some mustard seeds in each of them. Water the 3 beakers and wrap 2 of the beakers completely in red and blue paper each. Do not wrap any paper around the 3rd one. Place all 3 beakers in sunlight. Observe them after a week. You will see differences in the growth and height of the plants. In the beaker that was not wrapped, most seeds are seen to have grown well. In the beaker wrapped in red paper, you will see that only a few seeds have started growing, but those which have grown are tall. In the beaker wrapped in blue paper, many more seeds will be seen to have started growing, but these seedlings are somewhat shorter. This tells us that different colors of light have different effects on the growth of plants. Now, let us see how plants produce food using sunlight. Plants need light mainly for producing food. The